Good morning, everyone. Nice to see you. Welcome to Tuesday of week 9. So our third last lecture, which is pretty crazy. Again, a pretty short lecture today. I guess the only big updates are that auto marking is pretty much done. The short answer is what happened was that when we ran the auto marking scripts, we got slightly different outputs sometimes, and that was a little concerning, right? Because it's your marks and all of that. So we're going to release it last night, and I just was like, I don't know how I feel about this, because I feel like there's some problems here. So I I just spent last night trying to rewrite a bunch of stuff, and I'm mostly done. So it should probably honestly come out like 1 o'clock or something. I wrote 10 p.m. in the thing to give me some leeway in case I didn't make much progress this morning, but it seems to be okay. Yeah, so that's exciting. I won't talk more about that because it'll all be written up. But today we pretty much have property-based testing to talk through, which honestly isn't much. It's probably going to be one of our shortest lectures this term, and we can do a teamwork Tuesday if you'd like. I don't mind, or we can talk about other stuff as well. So 9.3. This is a topic that another lecturer put together a couple of terms ago called Rob, who I used to teach this course with. And it's in the bucket of SDLC testing, and it's a type of testing called property-based testing, which are essentially using tools to help you have a more varied type of input when you test, right? Because when you test, rather than randomly just typing in names and letters and stuff, you can use more automated ways to deal with that. So first thing is, what's the testing about the problem? What's the problem with testing? Or more specifically, what's the challenge of writing great tests? So testing is a great way to make sure that your software works well, right? It's better than linting, for instance. It's better than manually clicking stuff. The problem, though, with testing is that, as you know, it takes a long time to write a lot of tests. It can be easy to miss edge cases because your brain's not always thinking about edge cases. And this only gets worse and worse with larger and more complicated systems, right? For simple things, it can be okay, but for more complicated things, it can certainly be pretty messy. So, what we'd ideally like to do in some cases is, rather than us have to go and manually write out all of these pi tests, it would be really great if we could make a system or a computer do that for us, right? If we could get them to generate tests for us. So we would love it if a piece of software is able to generate test data, and then maybe help us report failures in an understandable way, right? Because if you generate test data, you generate 10,000 strings, for instance, which we're going to do. You need to have a way to actually test if that's working. So how do we automate away some of these processes? I know some of you have done 2521, some of you are doing 2521, some of you haven't done 2521, but there's a particular type of sort that's covered in 2521, which is called a bubble sort. And a bubble sort is a child sort, which we've all probably done. If I just gave you, if I just told you to sort numbers really naively, then an easy way to go about it is to basically just keep sweeping through the numbers, and every time they're in the wrong order, swap them. Right? So in this case, 5 and 6 are in the right order, move on, a 6 and 1 in the right order, no, so we swap them. This thing's looking a bit roundabout. We swap them again. Here, you just kind of keep going through it and swapping them until things are good. Here's another visual demonstration of it. You're just always swapping numbers as you go along. And eventually, if you cycle through this enough times, you get a sorted list of numbers, right? It's very slow, but it's very, very easy. And it's one of the simplest sorts to write. So again, I know there's a bunch of you that are I know what a bubble sort is. And then there's a bunch of you that are I don't know what a bubble sort is. But it doesn't matter if you understand the technicality of it. Conceptually, it's pretty straightforward. Swap. Swap. Swap anything in the wrong order. Right. And then start again. Swap. And do that until it's done. So that's what this sort is doing here, right? We have a Python bubble sort. And Generally, bubble sorts require 2 for loops because you've got the outer for loop that has to go through it, like just sweep it lots of times. As in, like, say you sweep it, well, you're going to have to sweep it many times. So you need 1 for loop to go through it and another for loop to have swept it many times. And that's what these 2 for loops are for here. And then this loop here is a swappy. So this is the actual, like, checking if 2 adjacent numbers are the wrong way around and then swapping them around. You can actually see there's a really cool piece of syntax you can use in Python here, which is like in a normal language, in another language you'd have to type in like a temp variable, right? Like if you're trying to swap 2 numbers, you'd have to make a temp variable, but like Python has this funny thing where you can destructure 2 values into the opposing ones here. So basically this is like swapping them, because we're kind of like saying that, hey, the tuple of these 2 values we're going to destructure into the opposite ones here. So that's actually how we swap those numbers, which is kind of nifty and neat. So we have this bubble sort, and we could test this out if we want. So I'll do that now. I'll call it bubble.py. We can put this in here. I might open my good friend Sublime. Okay, so we've got our bubble sort. Let's now we can try and run it if we want to. We could say, if name is equal to main, then we would like to say print bubble sort of a bunch of numbers. Like that. Python 3 bubble. Okay, there's our sort of numbers. Great. How would you write tests for this, right? This is where we're going to get into property-based testing. So if I said to you, go and write tests for this, the problem is you'd have to kind of sit down and write out a lot of different tests, right? Like I just wrote a bunch of random numbers then. Then you need to sort those random numbers, which, maybe you'll do right, maybe you'll do wrong. And then you need to write a lot of them to make sure it works and deal with all the edge cases, right? So it's very hard to write good tests, is the point we're getting at here. Property-based testing is essentially a method of testing where tests are defined as general properties. Now, these are some big words, but basically what this is saying is it's a little bit like fixtures, in the sense that how with fixtures you define like a function or like a capability as a property, right? Like if you have a fixture in PyTest, you just you write like def test something. You kind of just say PyTest.fixture. You put this above something else, and then you just say like values or something, or blah blah, and then you use that as if it's a property. But in actual fact, it's not a property, it's a function that's run and executed for you, and you've captured the return value, right? So this term property-based testing, if you're struggling to ground yourself, think about PyTest fixtures, because it's a similar thing. We use a variable we treat like a property that actually is a bit more complicated than that. It's not quite the same, but that's the closest thing I can think about. And what happens is that it generates test input automatically for you, and then the testing framework runs a bunch of times on all those different inputs and whatnot. But we can get into the practical element of it. So first thing, let's rewrite this as a test. So if I rewrite this as, say, def, test sort simple, like this, and then we can just assert that bubble sort here is the output of that's equal to 1, 2, 3, 3, 3, 4, 5, 6, 6, 8. And then we'll just double check that. So we can run PyTest on that. No test ran. Oh no, because it's not written as a... Alright, let's import the damn thing. Let's do it properly. Bubble test.py. Okay, from bubble import bubble sort, and then we'll call bubble sort like that. Perfect. Okay, so property-based testing. Now, probably the most popular property-based testing framework for Python, or at least one of the common ones, is a library called Hypothesis. It's not a massively used thing. I mean, this is not a huge topic. It kind of came into the course, I guess, because Rob had a Rob has a formal background in programming languages and takes a lot of interest in this. And I remember at one point we had a call. There's a guy in Canberra at the ANU, Australian National Uni, that is a contributor to this. So it's I mean, Python's a great little community of people. And the name of the thing we're using is hypothesis. So you can do a pip3 install hypothesis. I believe that it's part of requirements.txt. Let me just find that link because I've already lost it. I believe it's part of the requirements.txt we give you. By the way, because I know it's not obvious to people, so there's actually a second file here called requirementsextra.txt, and what requirements extra is it's modules that work on the runner, but we don't need everyone having to install, right? So the whole point of giving you this list is so that everyone in CSE can install all of these, so that all the labs and all the tutes and all the projects just work, right? We want everyone to have all these libraries installed. This is a list of libraries we don't care if you install, but you can install and know that it still works on the worker. This isn't something that really is massively concerning for people, because we usually add stuff unless you don't need it. Anyway, so hypothesis is what we install. Hypothesis tests are parameterized with a decorator, which we've already talked about, to supply strategies. Oh no, where's my code? Okay, one sec, I might have lost it. That's really weird. See bubblesort.py. Did this move weeks? Or sorry, I've lost something once again. Ah, great. Okay, there it is. I should really put that in the right spot. Copy or move bubblesort.py. This is the problem. I always change around content and I confuse myself. Okay, /week 9. Okay, so we'll go back to week 9. We got this bubblesort file. I'll call this bubble hypothesis testing. Now, granted, all of the tests are actually inside this file here, so I actually probably, what I probably want to do is actually put it inside my test file, and then we can still import our actual function. So we probably don't even need this file here. Okay, so I got my bubble sort file, which we've talked about, which is actually us using the bubble sort to sort stuff, and then we're testing it, and I've written a really basic test here already, right? So this is what we ran before, just a simple test. But what we'd like to do is something a little bit more involved, and I'll get rid of a lot of this to start, which in this case is going to be this test here. So I've got my simple test here that I wrote, which is like the test you write, and then I've got a property-based test underneath. So again, what does property-based test mean? Well, what's the property here in the property-based test? The property here is nums, because our test is taking in this magical variable called nums, but what's actually happening is the decorator, because remember how decorators work, they wrap a function, is going to create many instances of this test with lots of different inputs for nums. So this is going to run with literally, I mean, maybe I can print it out, nums, and we can have a look at it. So we're giving it two decorators. The first one is settings. You can add settings to a hypothesis test, which is basically saying to it, how much information do you want? So this is all coming from the hypothesis library, and then I'm importing a series of properties. Now, if I type in hypothesis verbosity, you can actually see there are different levels. Verboseness is how detailed and much information there is. And hopefully they give me a list of, why do they do this sometimes? I don't like it when you look up docs and they're like, yeah, here's the default value, but we're not going to tell you what the other things are. Okay, great. Thank you so much, Docs, for this insight. Verbosity, though, will generally kind of be like silent, normal, verbose. Like there's a few different levels. A very similar usage of this is like a Python log library, which is kind of like how you think of it like how you how you print, but you don't want to print it to terminal. There's like loggers you can use that actually print it to a file or somewhere else, and they often have different log levels. So like log levels are kind of like the extent to which you want to print out types errors. So this is like similar to verbosity in the sense that if you have a log and you have a setting of off, then it won't print anything. If you have a setting of fatal, it will only print you if the entire program crashes. If you get error, then it's like crashes or errors, warnings, there's crashes, errors, or warnings, info. And as you go down kind of this way, it's like more and more less critical, but then you get more of it, right? So verbosity.verbose is kind of down this bottom end here saying log and print as much information as you possibly can. So now if we run this PyTest, might make this window bigger. So you can see it's a little bit slower, right? Because it's doing some setup that it wasn't doing before. At least that's what I imagine is happening. Oh, it's a bit slow. Some YouTube questions. Griffin. Oh, sorry. No, that wasn't a question. Kira-chan says the problem isn't with the auto marking. That was very funny. I think overall groups did well. Like what we did was we piloted, we coveraged, we ran your tests against your code, we ran your tests against our code, we ran our tests against your code, and all of those except for that last one, people did generally pretty well in, because we were quite lenient on how we marked your tests against our code. In terms of like we didn't expect much of you. Your tests against your code, most people pass because it's deterministic. You can do that before you submit. Coverage is a similar thing. Pilot's a similar thing. Most people just lose a lot of marks in the our tests against your code thing. Did I screw something up here? How strange. Alright, let's try and get that back up. Or has VLab just had it with me today? Is it like I'm done? Okay. Maybe it's done. Oh, no, it's grumpy. I might have to restart VLab. Oh no. Who's Rob? Rob is another lecturer at CSE. They don't teach a lot, but yeah, I took over 1531 19T3, and Rob did it with me, and I did it the next term. Then I did it by myself last term. Rob used to be your tutor. How old are you? I don't know how long it's been since Rob tutored something. You sure it's Rob? I don't know. We were a little bit nicer this time around. I think just while I'm sorting this out. With your automarks for the project, one thing that we did do when we ran your tests against our code is that I didn't... Okay, so normally when you run your tests against our code, we delete everything but your test folder. Because like the dumb screw-ups that most of you make are like, I'm going to have my tests import from source and use some other random stuff, and you should be keeping them all separate, right? A lot of people would lose a lot of marks if we did that, but we didn't do that. So please don't get all... This is the thing, I think it's probably the thing that annoys me the most, I think, I would say, about auto marking is like, you do all these things when like students probably don't deserve marks, but you like give it to them anyway because you're like, oh, let's be nice and let's throw an olive branch. And then you get like an email from them and they're like, how dare you take off 0.01 of a mark from me in this area? This is so unfair. And it's like, I mean, I can be fair if you want, you know, like I can it can be like quite fair, but you know, we like to try and be good people. Let's try this one out. I legitimately have one student in 20T1 who came up to me and was like, my tutor marked me horribly and unfairly. Can you remark me? And they like wouldn't say no. And I was like, sure, I'll remark you. And a funny thing, right? Like their tutor was too harsh to them in this section, but their tutor was like way too kind to them in other sections. So like I felt bad because a student came to me and was like, can you remark my stuff? And I was like, yes. And then they got a lower mark afterwards. And it sounds horrible, but it's like this really tricky thing with marking in general is that it's actually very hard to ensure that tutors mark exactly the same for exactly the same things, because there's like, unless you have a really prescriptive criteria, which is hard for these like more interesting projects. So your main objective in my view as a lecturer is to like make sure that the tutors mark within a very reasonable range of each other, but more importantly that overall they're all roughly the same. You know what I mean? Like if a tutor gives like 1% more here and another tutor gives 1% more there, as long as like they all kind of balance each other out as a critical thing. If they're way out, then it's not good. Don't thank me yet. I mean, get your marks back first before you feel happy about things. It's just I had a preliminary look at the ones when I woke up because I had to run them overnight. And besides our tests against your stuff, they look generally okay. But please check it out. There's always a chance there's problems with our markers. Like, you know, we're fallible humans as well. And this auto marking is a lot more complicated because last time it was easy because you had your exact functions in the exact file we expect, whereas now we're running HTTP tests, so there's always chances that very strange things happen. Persistence as well, things like this. So, okay, let's try it. PyTest. I'm actually going to delete this thing here. Let's just make sure it works without that. PyTest. Okay, that works. Now let's add this back in. I can't imagine this having been the problem. Okay, good. 2 of them passed. Now, I don't get any prints, which is annoying, and you know this from PyTest. I'm sure you've all figured it out. I can't remember how to get prints from PyTest. PyTest print output. Some of you have probably figured this out. How can I see normal print output during PyTest running? -S disables per test capturing. I doubt that's going to give me what I want, but we can try it out. Ooh, no, that worked. Great. Okay. So, see, quick Google solves all your problems. All right. So look at this nightmare. So this is not the print happening as much as it's the verbosity. So the verbosity setting is, let me get rid of that and we can talk about this. So let me try this again. Okay, so here's what to understand. This given strategies list, this is the actual property-based test. This is a thing that's actually giving us random input to run with. The settings decorator is what's specifying to the hypothesis library how much crap should you print while you're running this. So for instance, if I run this without my print, if I just run this normally, then PyTest will just finish. Whereas when I add the verbosity up to verbose, which is the highest one basically, then you'll see that when this runs, it actually prints out a whole bunch of crap along the way. And it's actually very helpful. It's kind of saying here like, so this PyTest is being called literally this many times. So remember how we did that thing back in the decorators lecture where I showed you how you could write a function and you could make a decorator that actually calls it twice in a row? Think of this like this is the same kind of thing here, where a decorator here is actually like calling it for all the different types of tests it wants to do. And you can see some of the tests, you know, have 1 item in it, 3 items in it, many items in it, like this, more and more and more and more. So lots and lots of different tests. Now, how hypothesis works is the given decorator, which kind of runs this test many times, is given a strategies list. Basically, it's saying, give me a list of strategies you want me to run, and then we're giving it the strategies integers. Now, what strategies integers does is it basically is a strategy that generates a bunch of integers. So we're saying we've got the strategy that generates a bunch of numbers. then we're giving that to this strategies list thing, which is kind of weird. And then we give it to the given, and that actually tells it to do something. So if I go hypothesis, strategies, integers, hopefully we can play with this, right? So let's look at this integers. Hypothesis, strategies, integers. Great. Okay. And now you can see here that this strategies.integers function has a minimum and maximum value that we can run, right? Okay, great. So now I could tweak this. I could say, actually, I only want to test numbers between 1 and 10. Run this again. Let's look at the output. Okay, all the numbers are between 1 and 10 now. Perfect. So the strategies.integers part is specifying how to generate the actual elements themselves. The other part here is the strategies.lists. So what list does, right, is returns a list containing values drawn from the elements inside of it. So lists here generates lists based on numbers that are generated here, right? So you got to think of these are abstract functions that generate things. This one generates a number, right? Think of it like a random number. This one generates a list of what you give it, which is the random numbers here. So similarly, you can see the list thing, it takes in a bunch of elements. I don't know what the star means, genuinely. And then it takes in a minimum size. Oh, I don't know. But these are, remember how we talked about with the decorators lecture 2, how we have like keyword arguments and positional arguments? So you can see here, I can actually specify the keyword arguments of minimum size and maximum size. So if I want to here, for instance, my list, they get their elements, and then I can say min size equals 2. So I want a list of min size equals 2 and max size equals 4. Okay, now I can run this again. So now all of our lists have numbers between 2 and 4. So we can actually control these. We can use the hypothesis library to just very specifically get what we want out of these tests. So this is cool. How do these tests work? Well, the tests are pretty light at the moment. What happens is we basically get our nums, right? Because remember, this test is called for every one of these, right? So this test, it's not like your test that's called many times because the decorator does that. Yep. Quip says, are the generated test inputs deterministic, or are they different each time you run the test? I think they're different. I think it's random. It's a great question, though. How do you make it deterministic? I don't know. I've never thought about that. It might not even be... Hypothesis, strategies, deterministic, or maybe non-random, or... Oh, that's not good. Maybe I'll put Python out the front. Random. Ugh. I don't know. It's an interesting question. I've actually never thought about that, to be honest, because I only used this library once or twice for something, and I didn't really care whether it was random or not. I mean, it makes sense why you'd want it to not be random, because in theory, if it's random, the problem is that when you run it, it could like fail sometimes and succeed sometimes, right? Because that's the tricky thing about random anything, right? Is that you can have something... You can have tests succeed 1,000 times, then when you get a particular random seed that produces the particular edge case you don't want, then it will fail. I assume the point of hypothesis library in general, though, seed makes sense. I wonder if there is a seed somewhere. Maybe. I'm so curious why the hypothesis engine handles something state for the always seeding them to 0 and restoring the previous state after the test. So interesting. I'm just doing this because we don't have a ton to go through today. It's my distribution non-random. I don't know. So interesting. Just reading through the chat again. Um, reproducing failures tab of that page. Okay. Ah, great. That's what's I was wondering what you were saying with @seed, Trent. Thank you. Okay, so I don't know if we talked about random numbers in this course. I don't think we did. Oh god. But basically, random numbers are a funny thing because, great. So when random numbers are generated, they're generated by this thing called a seed, which is basically, it's kind of a funny thing. It's like your seed is like a true random number. So if I give you a number 0 and I say this is your starting point, every number that random functions typically generate after that is totally deterministic. As in, if you start with this magical number of 0 and then you generate random numbers, you'll always get the same list, right? So see how this is a random list of numbers, but it is deterministic in the sense that when I run it again, I get the same output every time. So if your starting point's the same when you generate random numbers, then your output's going to be the same, albeit the output of random numbers is just with respect to some starting number. So typically seeds are more random things associated with the physical world, like time, or there's some other things I don't fully understand. Like that, what's like random numbers and I don't know. I remember like was it? There's something about, I haven't read this for years. Someone else will probably know this. It's like if you squeeze a stone or something, it generates a random number. I don't know if I dreamt that, but there's lots of like natural things like time that you can rely on because the universe is seemingly random, right? Obviously nothing is truly random. So in general, like an example of a seed might be a Unix timestamp, right? So instead of setting a seed to 0, which gives me the same numbers every time, which isn't very useful if I'm trying to do something associated with security, I could maybe, do like, what is it, like Python date time in seconds. And I'll get, you've all probably worked with this, datetime.datetime.now / total seconds. Right, so if I import datetime, oh no, what have I done? I'm not doing it correctly. Oh, this is why you don't. Oh, that's for the time diff. Oh, that's very confusing. Timestamp. Okay. .today.timestamp. Read the docs, guys. Don't jump to conclusions. Okay. So this one's now kind of random, right? We end up with 111, 227. At the end, I'm looking at the last numbers. These are all random because the input is a timestamp, and that timestamp varies. Now, timestamps are not a very safe seed to use because someone can predict that, right? Like if someone's trying to hack you, then they'll just like be like, what time is it right now? And they could maybe have a guess, particularly if it's a seconds, maybe if it's like something more like milliseconds or microseconds, it's a bit different. Reading the chat, so HDSQ says that Cloudflare, which is a massive web host, how would they describe themselves? They're big. They're like cloud infrastructure. Yep. Think like Amazon Web Services, Azure, stuff like that. Anyway, so HDSQ says that Cloudflare generates their random numbers using tens of thousands of lava lamps. So I don't know what you mean by that, but if I can, and you probably do, if I can just guess, I'm imagining that something like that as an example would be, they have all these different lava lamps around and they must have some light sensors or something. That are just like picking up, or something like color sensors or something, surely. Like, and this is where most random numbers come from. I'm waiting to see if they know the specifics, but it's like you're essentially trying to observe a natural phenomenon, right? Like if you got a light sensor and you pointed it up at the sun, right? Then what happens is that the sun's going to give you different energy per day. But in particular, it's when the clouds come over. So if the clouds come over, then you're going to get some crazy random readings, right? Like no one can predict how much light down to like the millionth degree of light you're going to get from like random cloud cover. But if it's a sunny day, it's pretty easy to predict, right? So things like that wouldn't be good because under certain circumstances they're fairly deterministic. But we draw upon the natural world to try and look for these random things because you can't ask a computer to generate a totally random number very easily. You need to kind of give it some basic random thing for it to apply its somewhat deterministic randomness to. So fascinating topic. But anyway, the point is that without a seed, the computer does that for us. So if you wanted to say test this and you cared about it being the same every time, you'd give it a seed, and it doesn't really matter. It could just literally be 0. It could be 1, 2, 3. So I give it a seed of 0, I get the same every time. Great. And then I'm controlling what I give it, which is like integers. I could also probably give it floats or something. I don't know what this one is, if this even works. Yep. So this one's giving it floats instead. So if you wanted to sort with floats, now you can just do that. Really easy to write more and more tests. But I'll stick with integers for now. So again, the point of this property-based testing is that it's allowing you to define these really thorough, really diverse sets of tests in terms of inputs with just a couple of clean decorators. Less code you write, the better. Now, the last thing to check... oh, sorry, I'm just reading. They use the positioning of the bubbles in the lava lamps. Oh, that's interesting. Freaky. Okay. Yeah, it's really weird. I hope they still teach it in 2521, but there's a whole bunch of very strange natural phenomenon that just we can't model with a computer very well. Like fluid dynamics is another good example. Contract for difference, Jesus Christ. Like computers are actually really terrible at trying to simulate air because this physical phenomenon is way too difficult to model. And you need like supercomputers to do even like really basic things like this. It's a really interesting topic. When I say there's a set of problems called NP-complete problems, I'm just not sure if they talk about it. But basically in computing, it's really strange. There are two types of problems. There's like, well, there's more than that, but it's like there's solvable problems and unsolvable problems, right? And that's like, these are some unsolvable problems. Basically, they're exponential problems to solve. I don't want to get into it, but it's very easy to solve them with very small things. It's very easy to maybe predict like you could probably use a supercomputer or something to predict like the bubbles on one lava lamp, but to do it on like 10,000 is just impossible. So also, if there's a funny picture and there's a cow, someone tried to figure out how aerodynamic cows are. I don't know why I find this picture so funny, but I do. Okay, so back to this. What does this test actually do? It's actually just testing if the length of the input's the same as the output, but we can do better than that. We actually know that there's a sorted library in Python which will sort numbers for you, right? You've probably used it at some point. It takes in a list of numbers and it returns the list of sorted numbers. So, for instance, here I could do another assert, which is that the length of bubble sort, or I could say that the output of bubble sort nums is equal to the sorted list of nums. Now you might be thinking, what's the point of this? Like, how can we test, like, aren't we meant to write a sorting algorithm? Yeah, you are. Like, if this was the first sorting algorithm in history, then you couldn't do this, right? Like, you're using someone else's sorting algorithm to test your own. Which is actually really interesting because one thing that you actually do a bit, and I've done this before, is that sometimes when you're writing tests for things, if you need to write a really complex sorting algorithm, sometimes you'll actually write a simpler sorting algorithm that you can verify by hand, like a bubble sort, because it's so simple, so that you can then test your code against your own code. right? So that's an approach if you're ever trying to test crazy code where you don't know how to check if the output's correct, right? Because like, how do you check if a million numbers are sorted correctly if you don't have a sorting algorithm? Write a simpler one. Write something so simple that you know it's correct, so that you can do something like this. So now when I run this one, great, 2 tests have passed. Just to be more specific here, I should be really clear. So these decorators don't necessarily run this PyTest test many times. As you can see, we still only run 2 tests. It's the fact that it actually kind of runs many asserts within that test, just to be clear. So anyway, that's the hypothesis library. We've written extremely thorough tests now for our bubble sort. Very powerful. You can't use it a ton, right? Like you can't use it for some things, but you know, things like password generation, I don't know. It's something you can definitely use in your project, just not extensively. Message send, for instance, stuff like that. So you know, it's something if you're interested, you can check it out for iteration 3. It's not expected. I don't really teach anything that I expect you to get done in less than 7 days. So, but you know, I know there's the odd group out there that's kind of curious about it. Okay, so sorry, I'm just making a note. That's it. Any questions about property-based testing and using this stuff? It's another case of there's a library out there that does a bunch of things that you can always look to if you'd like. You know, it's kind of up to you. Otherwise, we'll wrap this one up. HDSQ, I'm actually so worried about our HTTP routes were so lacking it'll be impossible for them to actually test the backend implementation, which is sad because you put tons of effort into that. I mean, it's a little bit sad, of course, but I think something to just put in perspective is, you know, us testing your backend is like 35% of this iteration, right? And this iteration again is 40%. So that's, you know, 14-ish% of the project, and the project is like, you know, half the course. And like, you know, that's still like, even if someone gets 0, that's still 7% of the course, right? Which is pretty negligible. But there are lots of assignments at uni which are pretty like heavily auto marked, where they're like 80% auto marks, and like you can literally just like knock 25% of the course out, especially when you feel like you've learned less. So I'd say good luck, and if things are bad, it's not a death sentence, is kind of my point. Like, you know, pick yourself up and keep going, and we'll get through the end of the course, and there's always room to improve in iteration 3. Okay, thanks for 9.2. I'm going to send the poll out.